Okay, so I did this while I wasn't recording accidentally. So the chapter 10 here deals with matching problems. And the lead problem is we have 300 boys and 300 girls such that each boy knows exactly 50 girls and vice versa. So each girl knows exactly 50 boys, and also knowing is reciprocal. So a boy can't know a girl unless she also knows him, and vice versa. Is it possible to have each boy dance, every boy and girl dance with someone of the opposite sex that they already know? So we're not trying to introduce any two people here. We're just trying to pair them up with somebody that they already know. And it's bipartite, where we're using traditional sex differences here. So boys on this side, girls on this side, and each of them has regular degree 50, and we want to know, is it possible to pair them up that way? And it turns out, yes, we can, because of Theorem 10.1.1 in our book, which says if a bipartite graph has all vertices, or has all vertices of the same degree greater than or equal to 1, so we can't have degree 0 for everything, then there exists a matching. A matching is just a way to pair up everything on one side of our bipartite graph with something on the other side of the bipartite graph. So in the end, we get a subgraph, basically just deleting a ton of these edges in the middle, such that everything is of degree 1. So another question that your textbook has in 10.2 is, if we've got a map of an area such that each of these guys is split up into groups of, say, 100 square miles. So now we've got 1, 2, 3, 4, 5, 6. Cool. Yeah, let's just do that. Each of these is 100 square miles. And then there's another overlying map that each of these guys is also 100 square miles. 1, 2, 3, 4, 5. Is it possible to pair up each of these regions? So that's essentially what it's asking. As your textbook frames it, there are 6 tribes that each have hunting area that takes up 100 square miles. And then there's also 10 different types of tortoises that don't overlap with each other. Their territories don't overlap with each other. And each tribe wants to pick its totem as one of the tortoises that are within its territory. And is that possible? The answer is yes. And that is because of Hall's matching theorem, or marriage theorem. It goes by either name. So basically we can look at these guys, and if I call this A, B, C, D, E, F, and then I call this territory 1, 2, 3, 4, 5, 6, then I could create a bipartite graph. Bipartite graph here, such that I basically just look at the overlap between them. So A overlaps with 1, 2, 3, and 4. So that means that tribe A's territory intersects with those first 4 species of tortoise. B overlaps with 2, 3, and 4. C overlaps with 3, 5, and 4. And I really hope that this works out because I didn't measure out anything, but I think it should. So D overlaps with 4 and 2. So D overlaps with 4 and 2. E overlaps with 5, 6, and 4. 4, 5, and 6, as we normally say those are the numbers. And then F just overlaps with 5 and 6. So we are guaranteed, we should be guaranteed in this case that every single, that there is a matching, because for Hull's matching any subgraph, there exists a matching if and only if, that IFF just means if and only if, there for each subgraph or subset of one side, it is connected to, so each subset A connected to the set B. Set B, then we have the cardinality of A is less than or equal to the cardinality of B. So there's a matching if and only if this is the case. So A is a subset of these guys, and then B is a subset of these guys. So I'll call this guy alpha, and this guy beta. So so let's prove this result. So let's prove that direction. Assume there exists a matching. Then cardinality of A is less than or equal to the cardinality of B, because B contains all of the elements, the vertices, that A connects to in our matching. That A connects to in our matching, plus possibly some others. Therefore, B is greater than or equal to A, or the cardinality of B is greater than or equal to A. The opposite direction is also pretty easy. So we assume for all subsets. So here A is, let A be any subset of alpha. So we assume for that for all subsets of A, all subsets of alpha A, then the cardinality of A is less than or equal to the cardinality of B, and we wish to show that there exists a matching. So here, this is what I'm trying to show, but instead I'm going to try to show the contrapositive. I think that's just going to be a little bit easier. So there does not exist a matching implies that contrapositive of the statement is there does not exist a matching implies that there exists a subset A such that the cardinality of A is greater than or equal to the cardinality of B. Right? So this is just the statement of the contrapositive, and this is going to be pretty easily shown to be equivalent to does not exist a matching, because if there does not exist a matching, then I can just keep on removing vertices from A until I get a subset such that we have more elements of A than we have of B. So basically, we can just we have up until we get something that, if I actually attach this isn't a great drawing to depict this, but basically we can eliminate an edge from A such that it doesn't create any redundancy. It doesn't eliminate anything over here. And this is an example of something that doesn't have a matching.